Hello class, this is CSE-4600, Section 1, Week 13, Spring 2025. Last week we began our discussion on resources and deadlock. So, your computer system, your operating system as a resource manager, your computer system consists of resources that a process needs access to do its work. And the operating system's role as a resource manager is to divvy out those resources in a way that prevents deadlock. Deadlock happens when the progress of one process is blocked by another process, which in turn is blocked by the previous process. Kind of like how these cars are trying to move forward, but they're all blocking one another. So the operating system's job is to keep this from happening, or detect that it has happened and roll back to break the deadlock however it can. So we began our discussion on resources. Those are just anything that a process needs to use to do its work. Anything that must be acquired, used, and released over the course of time. This can be hardware such as a disk drive, a printer, or it can be information such as a file or a record in a database. Resources are either preemptible or non-preemptible. Preemptible meaning we can take it away without any issue, and non-preemptible meaning the opposite of that. If you try to take it away, bad things may happen. If a process needs access to a file, but it's only reading from the file, if you take away the file from that process, all you've really done was delayed that process's ability to read from the file. Basically, it has to wait its turn again. Which is a non-issue if you don't mind waiting a little bit longer for your turn to read the file. If that process was writing to the file, if you preempt the file, then there is a possibility that you now have inconsistent data written to the file. You might have inconsistent stuff written to the file, or worse, you might have file corruption, which is bad. The CPU and memory are prime examples of preemptible resources. The CPU as a resource, all your processes take turns on the CPU. And the way this is possible is when it's time to context switch from one process to another, the values in the registers on the CPU, they're saved so that when it's time for that process to run again, we just put them back in the registers like nothing even happened. It's kind of the same deal with memory, where memory is used to store the code for the program if we need to make room for another process. Depending on whether that, because of how each process has its own independent address space and how pages are stored on a backing store, if we need to make room for more processes, or if a process goes idle and we need more page frames to be available, we can just save those pages onto the disk, and when page frames become available, we'll just take those pages and put them back into a page frame. So memory and CPU are preemptible. Though that also depends on the system, because for some systems may not support paging, and if that's the case, then memory is a non-preemptible resource. Because if we need to free up memory, and there's stuff in memory, where does that go? There's no place for it to go. So, processes need to acquire resources. This can be done through system calls, or this can be done through semaphores. Recall that a semaphore is a value that indicates how much of a resource is available. The two operations associated with it are down and up. Down decrements the available resource by 1. Up increments the available resource by 1. So if you need a resource, we call down. And if that value was 0, if you call down, if a process calls down on a semaphore whose value was 0, that process goes to sleep. That's because there's no more resources available. That process must wait its turn until resources become available again. If another process calls up, that resource becomes available again. That sleeping resource wakes up, realizes, oh, there's a resource available, and then that process can continue with its work. This code here, there are two versions of the same code, and these are two processes accessing two different resources. The long and short of it is, depending on the order in which you request for resources, may result in deadlock. So here's how it works. And I am going to use the standard symbols used to represent processes. Let me just... Here we go. Okay, let's do it like this. Process A and process B. Process A needs resource 1. Process B also needs resource 1. Process A also needs resource 2. Process B also needs resource 2. So these arrows from process to resource, that means a process is requesting a resource. So now we have two processes fighting over resources. Are they? Well, only one process at a time can get that resource. So who gets the resource first? Let's just say it's whoever requested it first. In that case, because A requested it first, process A actually gets the resource. So what happens next is we take this arrow and we flip it around the other way. This denotes that resource 1 is allocated to process A. What happens to process B? Well, it waits its turn. And now process A also needs resource 2. And let's say it was also the first to get to it. So that arrow also reverses. So now process A now has both resources 1 and 2. Process B waits its turn. Okay, so process A got all the resources and it's greedy little. And now process B must wait its turn, and that's okay. Because process A got the resources, it's going to use them, and it's eventually going to release them. Once process A is done with its resources, it's going to release them. So I'm just going to denote that by erasing all the arrows. Once process A is done, then now those resources are available for process B to use. So we're going to denote that by reversing the arrows. And now process B has the resources. Eventually, process B uses the resources and then releases them. And I'm going to denote that by erasing the arrows. Erased. And erased. And now we have process A. Process A's job is done. It used the resources and now it's done with them. Process B was able to also get its job done. It used the resources and then it released them. So this assumes that both processes asked for resources in the same order. This is actually a spoiler for what's coming up next, where we try to keep deadlock from happening. What happens if instead this happened? So previously, we had process A ask for resource 1. At the same time, process B also asked for resource 1. Whoever gets it first, which we're going to be using for our tiebreaker, is the process that gets to use it. So in that case, if process A got it first, then resource 1 gets allocated to A. Process B must wait its turn. What happens if process B then asked for resource 2 before process A? And what happens if process B was able to get it? Remember, both processes need both resources to do their job. And now process A must ask for resource 2, but it's already allocated to process B. Now we have a problem here. Process A needs R2, which is allocated to process B, which needs R1, which is allocated to process A. A is not gonna let go to R1 until it gets R2. Process B isn't gonna let go of R2 until it gets R1. See the problem? This is deadlock. Neither process is gonna let go of what they have until they get what they want. Until they get what they need to do the job. So, this alone, this condition where we have this circular loop, this circular wait as it's called, that's one of the conditions for deadlock. Hey, if we just told process A, to let go of resource 1, would that be okay? That's called preemption. If these resources are not preemptible. No preemption. If these resources were preemptible, then we can easily break the deadlock. If we told process A, hey, let go of resource 1, we need, so process B can work. If we could do that without any issue, then that alone will break the deadlock. So that's actually one of the other conditions. No preemption. Couldn't these processes use a resource at the same time? Well, we're gonna make the assumption that no, they cannot. If two processes read from the same file, that's okay, but if two processes try to write to the same file, that's bad, because we might get conflicting data being written. So we cannot have a situation where two processes share a resource. So that's called mutual exclusion. The fourth condition is called hold and wait. Once a process gets a resource, it's going to hold onto it, and then it can request for another resource. So once a process gets a hold of a resource, it's going to hold onto it until it's able to get its next resource. So once a process's request for a resource is fulfilled, it's going to hold onto it, and then it's going to request for another resource. It's going to hold on to that and then it's going to request for another resource, and another one, and another one, until it gets all the resources it needs to do its job. That is called hold and wait. And those are the 4 conditions needed for deadlock to happen. Mutual exclusion, resources are available or assigned exactly to one process. Alternatively, it means one process at a time for each resource. Hold and wait. If a process has requested a resource, it's going to hold on to it, and then it's going to request for another resource. No preemption, meaning resources can only be released by whatever process is holding it. We cannot take away resources from a process. And finally, circular wait, which is probably best drawn in a diagram like this, where if we have a loop like this, that's a circular wait. If the other two conditions are met, we have deadlock. So those are the 4 conditions for deadlock. It also means if we can eliminate even just one, we don't have deadlock. If we don't have a circular wait, we don't have deadlock. If we can preempt a resource, we don't have deadlock. If processes can share resources, they don't have deadlock. If processes aren't allowed to hold onto resources that it's already acquired, then we don't have the deadlock. If we eliminate any one of those conditions, we don't have deadlock. I left off last week's discussion with strategies for dealing with deadlock. The first one is to just ignore the problem. The second one is detection and recovery. Let deadlock happen, detect when it happens, and recover it from somehow. The third one is deadlock avoidance. Allocate resources in a way that avoids deadlock. And the fourth one is preventing deadlock from happening in the first place by negating one of the 4 conditions for deadlock. Let's look at the first 2. I'm going to save the next 2 for next week. Okay. So as I said, there are 4 ways to deal with deadlock, and the first one starts with not dealing with it. This is called the ostrich algorithm, and it's the simplest way to deal with the deadlock. Ignore the problem and hope it doesn't bother you. Like how an ostrich sticks its head in the dirt to provide predation, which is of course absolute nonsense. An ostrich's kick is strong enough to shatter bone, and lions know better than to provoke an ostrich. Thing is, ignoring deadlock may or may not be acceptable based on how frequent it happens. If a serious deadlock only happens like once every year, why spend time and money to implement a system that would deal with it? On the other hand, if a serious deadlock happens like every other week, and someone's come in at 3 a.m. to break the deadlock, then maybe it's time to start thinking about implementing an actual strategy. The ostrich algorithm, for our purposes, isn't really a strategy. It's also based on absolute nonsense, so we're going to move on to an actual strategy, and that is detection and recovery. Here, the operating system does not attempt to prevent deadlock from occurring. It lets it happen, tries to detect when it does, and takes some action to recover from it. And there are 2 strategies based on whether we have one of each resource type or multiples of each resource type. We're going to look at 2 algorithms for this, by the way. And the first one is the simplest, where we have one of each resource type. So let's begin with an example where process A holds R and wants resource S. Process B holds nothing and it wants resource T. Process C holds nothing and it wants resource S. Process D holds resource U and it wants resources S and T. Process E holds resource T and it wants resource V. Process F holds resource W and wants resource S. Process G holds resource V and it wants resource U. Let's try that. So with an example like that, we can just draw the diagram. We can just draw a resource allocation graph and connect all the nodes accordingly. So process A holds R, and it wants resource S. Process B holds nothing and it wants resource T. Process C holds nothing, but it wants resource S, so I'll just draw it up here. Remember, a arrow pointing from a resource to a process means that that resource is allocated to a process. If an arrow points from a process to a resource, that means that process is requesting a resource. Process D holds U, and it also wants S and T. So I'll put process D up here. It's holding on to process D is holding on to resource U. And it also wants resources S and T. Process E is holding on to resource T. It wants resource V. Process F is holding resource W. And it also wants resource S, so I'm gonna have to draw it up here. Process G is holding on to resource V. And it wants resource U. Alright, so now we've drawn our graph. The question to ask is, which processes are deadlocked? I'll give you a minute to think about that, but the key is this. If we have a diagram that represents our resources and processes and how each process... If we have a diagram like this that represents how processes are requesting for resources and how resources are allocated to processes, then if we want to find deadlock, all we gotta find is a loop in the graph. Is there a path in this graph that goes in a loop? Do you see it? Do you see it? That's where I find it. Okay, so WF and it goes to S. This S resource is being pulled in like 4 different ways. It's like it's being drawn and quartered. Is that the deadlock? It's actually not, because only one process is going to use resource S at a time. So let's say C gets the resource. Now processes A, D, and F must wait their turn. But that's the thing. They wait their turn until C finishes, and then it's going to be available to the 3 remaining processes. So it turns out that S, even though it's being requested by 4 different processes, that's not our deadlock. So let's keep going. So resource S, that's not our deadlock, but all you gotta find is a loop. So look at process D. It's requesting resource T. Resource T is allocated to E, which is requesting resource V. Resource V is allocated to process G. It's requesting for process U. And it's allocated to process D, which is asking for T, which is allocated to E, which is asking for V. We find a loop! So this is our loop. If we find a loop in our graph, and it must be a loop, and the loop must be traceable along these one-way arrows, because these are one-way paths. So if we follow these arrows and we get stuck in a loop, that is our deadlock. So here we have processes D, E, and G stuck in a deadlock. So that is where our deadlock lies. For a small graph like this, where it's easy to draw the graph and figure out what processes are deadlocked in this way, yeah, it's easy enough to just draw it and find where the deadlock is just by following all the arrows. But it's a good idea to have a formal description of our deadlock detection algorithm because for larger graphs, it's gonna get complicated really fast. So here is the formal algorithm. For each node n in the graph, follow the 5 steps here with n as the starting node. Initialize L to be the empty list and designate all arcs as unmarked. Add the current node to the end of L and check to see if that node appears in the list L twice. If it does, that means we have visited the same node again. That means we have a loop. That means we have deadlock. For the given node, see if there are any unmarked outgoing arcs. If so, go to step 5. If not, go to step 6. Step 5 is pick an unmarked outgoing arc at random and mark it. Follow it to the new current node, go to step 3. Step 6. If this node is the initial node, the graph does not contain any cycles and the algorithm terminates. Otherwise, we have reached the dead end. Remove it and go back to the previous node, the previous node that we just at. Make that the current node and go back to step 3. What? Okay, let's do it one step at a time. So we need a list. So we need a list of visited nodes. Let's pick a node and start there. Let's start at node W. Doesn't matter if it's a process node or a resource node. Let's start at node W. Okay, so now we're at node W. And let's follow one of the outgoing arcs to a new node. Oh, but before we do that, let's double check to see whether node W appears twice in our list of visited nodes. No, it does not. So let's just follow one of the outgoing arrows to the next node, which is node F. Does node F appear twice in our list? No? Okay, let's go to the next node. So there's only one outgoing arc, and it goes to node S. Are there any outgoing arrows at node S? No. They're all going into S, but nothing's going out of S. So it means we hit a dead end. We hit a dead end. Let's backtrack. So let's go back. We're gonna remove node S from our list. We're gonna go back to node F. Are there any more paths we can take from node F? No. So we're gonna remove node F, and we're gonna go back to node W. Are there any more outgoing nodes at node W? No? Okay. Then that path started and hit a dead end. Let's try a different node. Let's try node B. Let's add that to the list and go to the next node. But before we do that, let's double check to make sure that we haven't already visited B. Does B appear twice in our list? No. So let's go to the next node. So I'm gonna mark this arrow by drawing it over with red. I can just put a little check mark on the arrow. And now we are at node T. Did we visit node T already? No. Okay, so now we're at node T. Let's follow one of the outgoing arrows to the next node. There's only one, so let's go to node E. Let's put a little check mark on the arrow to the node. We've already traversed that, traveled along the arrow. We're at node E. We have not visited that one already. So let's follow the outgoing arrow to node V. We have not visited node V just yet. This is the first time we visited node V. So yeah, I'm gonna mark that arrow, and now we're gonna travel to the next node, which is node G. I'll put a little check mark on that, and now we want to go on to node. We're now at node G. There's only one outgoing arrow, and we have not visited node G already, so let's just follow that. I'll put a little check mark on that arrow, and now we're at node U. We have not visited that node yet. We have not visited that node already. There's only one outgoing arrow. I'll put a little check mark next to that. And now we are at node D. Okay. There are 2 outgoing arrows at node D. Let's pick one. Let's pick this arrow, and now we're at node S. And now we've reached a dead end because there are no outgoing arrows on node S. That means we have to backtrack and try a different path. So I'm gonna take out S from our list of visited nodes, and then we're gonna go back to node D. Now we've backtracked. Let's try a different path. There were 2 paths that we can take at node D. We already took one to node S, so the only one left is the one going to node T. Let's follow it. I'll put a little check mark next to that arrow, and now we are at node T. There are no more paths that we can take, but check this out. We have visited node T already, and now we have node T in our list again. That means we have deadlock. We found deadlock in our graph. So this is the algorithm for detecting deadlock in a graph for which there is only one of each resource type. This is the step-by-step process of figuring out how to find deadlock in our graph. It's also shown in the slides. I'll demonstrate to you real quick. We start at node B, or we could have just started at any node and find a loop in the graph anyway. So we start at node B, we go to node T, then E, then V, then G, then U, then D. There's 2 different paths we can take at node D. Let's try one of them. We try node S, we go to node S, we hit a dead end, we backtrack, go back to node D, try the other path, and we go to node T, which we had already visited. This algorithm is a depth-first search algorithm. What this algorithm does is it builds up what is called a search tree, which is a representation of how this algorithm traverses this graph. If at any point in this search tree it encounters the same node, we hit a loop. And in our case, that means we have deadlock. A depth-first search algorithm traverses a graph and goes as far as it can on some branching path until it hits a dead end and then backtracks and tries a different path. Eventually that hits a dead end again, it backtracks, tries some other path. It backtracks, tries some other path, backtracks, tries some other path, backtracks, tries some other path. So it's going to go as far as it can down this graph, and for our purposes, it's going to stop if it encounters the same node twice, or it has exhausted every possible path. If this algorithm exhausts every possible path and visits every node exactly once, then our graph does not have deadlock. If it encounters the same node more than once, that means there's a loop somewhere in our graph, that means we have deadlock. Another thing is, this algorithm must try every node in the graph because it's possible to have disconnected regions of this entire graph, where some processes are deadlocked and others are not, and they're just unrelated to the deadlock. Can you see all the disconnected graphs I drew in here? Is this the best deadlock detection algorithm? It turns out it's not. There is another one, but we're gonna move on to our next deadlock detection algorithm, which is used for if there are multiples of each resource type. So, we could just draw another graph, but we're gonna do this using matrices and vectors. So, this is gonna sound complicated, but they're basically lists of how much of each resource each process needs. So there are 4 data structures. E, A, C, and R. The two vectors are the existing resource vector and the available resource vector. Vector E represents how much of each resource is in existence. Vector A represents how much of each resource is available, not allocated to any process yet. Matrix C, each row in that matrix is how much of each resource has been allocated to a process. So row N represents the current allocation to process N. How much of each resource has been allocated to process N. And that's the current allocation matrix. The next matrix is R. That is a listing of how much more of each resource a process still needs. Each row is a request for more resources by that process. So row N in the request matrix is how much more of each resource process N needs to complete its job. There is a property where if you summed all the columns in matrix C and then added them to the corresponding values in vector A, you get the values in vector E. And that's just a restatement of resources are either allocated to a process or available. Deadlock detection is based on comparing vectors. If we have a request for resources, so let's say process, give me a minute. Okay, so deadlock detection using this algorithm is based on comparing vectors. How about we walk through an example of what I'm talking about? Actually, let's talk about what it means for one vector to be less than another. If we have resources, vector A is how much of each resource is currently available. If we look at any one row in matrix R, that is a listing of how much more of each resource that process needs to complete its job. What it means for one vector to be less than another, if R21, this is for process 2, if R21 is less than A1, and R22 is less than A2, and R23 is less than A3, and so on and so forth, and R2M is less than AM. It can also be less than or equal to. If for each R2I, if every R is less than its corresponding A, less than or equal to its corresponding A, then that means this vector is less than this vector. So here is our algorithm. All processes are initially unmarked. If a process is marked, then that process is able to complete its work and eventually release its resources. The algorithm is as follows. Look for an unmarked process Pi, for which the ith row of matrix R is less than or equal to A. If such a process is found, add the ith row of C to A, mark that process, and go back to step 1. Step 3 is, if no such process exists, then the algorithm terminates. If the algorithm terminates with unmarked processes, then those processes are deadlocked. So let's draw this out. I'm going to reset this drawing once more. And now we have this example here. Where we have 3 processes, P1, P2, P3. P3, and this is also P1, P2, P3. We have three processes, P1, P2, and P3, and they all need different amounts of the same resources. Currently, process 1 has 1 of resource 3. Let me just label the resources. So P1 currently has 1 of resource 3. P2 has 2 of resource 1 and 1 of resource 4. P3 has 1 of resource 2 and 2 of resource 3. For those processes to complete their job, process 1 needs more of the following: 2 more of resource 1 and 1 more of resource 4. Process 2 needs 1 more each of resource 1 and 3. Process 3 needs 2 more of resource 1 and 1 more of resource 1. So let's ask the question. Given each row in matrix R is a listing of how much more of each resource each process needs, which request can be fulfilled right now? Can we fulfill process 1's request for resources? No, because we don't have enough Blu-ray discs, Blu-ray drives. Can we fulfill process 2's request? No, because we don't have enough scanners. Can we fulfill process 3's request? Yes, because we have exactly enough tape drives, and we have exactly enough plotters. Process 3 doesn't need any scanners or Blu-rays. So, really what should happen is process 3's request will be 0, it will be zeroed out, and then this available vector here will become 0, 0, 0, 0, denoting we have no more of those resources. And then, here, it'll just become 2, 2, 2, 0. But eventually, process 3, after it's done using all those resources, it's going to give them back, and all of those resources become available again. So what will happen is, instead of just 2, 2, 2, 0 here, it's going to become, if I can just draw this out, so instead of this row staying 2, 2, 2, 0, it's going to become 0, 0, 0, 0, and then this is going to become 2, 2, 2, 0. So, really what we should do is take this row, the values in this row, and then add it to this vector here. So, let me backtrack. Because we know that we can fulfill process 3's request for resources, what we gotta do is add these values to these values. And we can do that simply. So 0 plus 2 is 0, 1 plus 1 is 2, so this is gonna become 2. 2 plus 0 is 2, and 0 plus 0 is 0. Let me really make sure that this is correct. And there we go. It means we can zero out this row here, so let me just cross those values out. And because process 3's request is fulfilled, we can zero this out as well, but really what you should do is just put a check mark on this row, saying we can fulfill that process's request for resources. So now we can ignore process 3's request for resources because it can be fulfilled without issue. So now we have to ask the question, which process's request for resources can we fulfill next? Can we fulfill process 1's request for resources? Process 1 needs 2 tape drives and 1 Blu-ray drive. But we still don't have a Blu-ray drive. We're out. So no, we cannot fulfill process 1's request right now. Can we do process 2's request? Process 2 only needs 1 more tape drive and 1 more scanner. Oh yeah, we have that right there. We have two of each, but we only need 1 of each. So let's put a check mark on process 2. Let's zero out this row. But before we do that, let's add process 2's resources here back to here. So we're going to add 2 plus 2, which is going to become 4. 0 plus 2 is 0, 0 plus 2 is 0, and this 1, we're going to add it to here. So we're adding this row to this vector, and that's going to change our counts, the available resources, from what it was previously to 4, 2, 2, 1. And now we have zeroed out process 2's current allocation, because now process 2 is able to run to completion. And now we have 4, 2, 2, 1. Can we fulfill process 1's request now? It needs 2 more tape drives and 1 Blu-ray drive. Oh, we have that. We have all of that right here. Look, we have 4 tape drives available and 1 Blu-ray drive available. So put a check mark there. And once that's done, we can add that 1 resource back to here. So that's going to become 3, and this is going to become 0. And we have no more processes with outstanding requests anymore. That means we have shown that all of these processes can run to completion without deadlock. As a sanity check, let's make sure that our available resources matches our E vector here. So we began with 4, 2, 3, and 1 of each resource, and we ended with 4, 2, 3, and 1 of each resource. We have check marked all 3 processes. That means all the processes are able to run to completion. There's no deadlock! So that is the algorithm for detecting deadlock if we have multiples of each resource type. The thing is, not every process is going to use all of these resources. As you may have noticed, some processes don't even need certain resources. So check this out. Process 2 here doesn't even need a plotter. Process 3 here doesn't even need a Blu-ray drive, which is good because we're out of Blu-ray drives right now. Let's try a variant of the same problem where instead we had this. We're gonna run the same algorithm, except process 3 also needs a Blu-ray drive. Can we fulfill it? Let's try it out. Let me add our labels back here. There we go. Okay, so this is the same set of data structures E, A, C, and R, except for one tweak where process 3 also needs a Blu-ray drive. So let's try the same algorithm. Is there a request for resources such that we can fulfill it? Is there a row vector from matrix R that is less than or equal to vector A? Can we fulfill process 1's request for resources? Process P1 needs 2 tape drives and 1 Blu-ray drive. But we don't have Blu-ray drives, so no, we cannot fulfill that request. Process 2 needs 1 tape drive and 1 scanner, but we don't have enough scanners. Process 3 needs 2 tape drives, 1 plotter, and 1 Blu-ray drive. But we're out of Blu-ray drives, so the algorithm terminates and they're deadlocked because none of the requests can be fulfilled. There's deadlock, and now it means none of our processes can run to completion. So this set of processes is deadlocked. Okay. This is deadlock detection, and the next part of that is recovery. What do you do once you find deadlock? Well, there are a few things you can do. You can preempt resources, do a rollback, or start killing processes. In some cases, you can preempt resources, but you may need to do this manually in some cases, or at worst, it might not be possible to preempt resources at all. If you're gonna recover from deadlock through preemption, taking over resources, that depends on which resources can easily be taken back. The other option is to do a rollback. Some systems create a checkpoint. That is a file that includes the states of all processes, including what resources are allocated to each process. Some systems can save multiple checkpoints also. If a deadlock happens, just roll back to our previous state and reload that checkpoint file. At that point, try something else that would prevent a deadlock. All work up until that point is lost, but at this point, we can try something else to prevent a deadlock. So that's the point of doing a rollback. Go back to our previous state and see if you can do anything different that would prevent deadlock from happening. If all else fails, start killing processes one by one. So, which processes do you kill? Processes in a cycle might be a prime target, but sometimes it's actually another process unrelated that took all the resources for itself, so you gotta kill that instead. So, yeah, you might start killing processes in a cycle, but it might be more effective to kill other processes that took all the resources before those processes became deadlocked. Where possible, kill a process that can handle starting over without any ill effects. For example, if a process was reading from a file, starting over is okay. If a process was writing to a file, then you're gonna have to contend with interrupt values being saved in that file. So yeah, that is 2 of our 4 deadlock handling strategies. Ignore the problem and detect and recover. The next 2 are deadlock avoidance and deadlock prevention. We avoid deadlock by carefully allocating resources to processes in a way that keeps deadlock from happening. That is the goal of deadlock avoidance. You avoid a situation that leads to deadlock. And the 4th one is preventing deadlock in the first place by negating one of the 4 conditions for deadlock. So, we're going to look at the last 2 next week, and probably from there, we're going to finally get started on our final project, which is we're going to implement one of these deadlock-related algorithms. We're going to implement one of them, okay? Alright, so this is everything that was summed up from this week. No new assignments this week. Rather, I'll have something for next week, okay? Alright, so that's going to be it for this week. We have looked at 2 strategies for dealing with the deadlock. One of them wasn't really a strategy, but we had to talk about it anyway. Ignore the problem and hope that it'll ignore you. The second one was detection and recovery, for which there are two different strategies depending on whether there is one of each resource or multiples of each resource, and what to do once you find deadlock in the system. If you think about it, these four strategies are just building up on top of one another. The first one is to ignore the problem until you reach a point where it occurs so often that you can't ignore it anymore. So, you let it happen, detect that it's happened, and recover from it. So, detection and recovery feels like an upgrade over just ignoring the problem entirely. Deadlock avoidance now takes the extra step of going further. It goes further than detection and recovery because now you're taking steps to steer the system away from deadlock. So think about it. The first strategy is ignoring the problem. The second strategy is acknowledging that there is a problem and doing something about it. The third strategy is going further and actively steering the system away from situations that would lead to deadlock. And the fourth strategy is to go one step further and find a way to keep deadlocks from ever happening in the first place. We're going to look at the last two strategies next week. Okay? Alright, so that's going to be it for this week. Have a good one, and yeah, see you next week. Bye.